Hello everyone, it's 1 p.m. Eastern, and that means it's time to begin another one of our monthly CoCoRaHS webinars. Thanks for joining us today. I'm your host, Zach Schwalbe. Behind the scenes today, running the technical side of the program, is our CoCoRaHS for Schools dude, Noah Newman. We're coming to you live from the Colorado Climate Center here at Colorado State University in sunny and chilly Fort Collins, Colorado. For those of you who are unable to join the webinar, for our live broadcast, we'll be recording for future viewing on our website. All of our WxTalk webinars are sponsored by grants from NOAA's Office of Education and the National Science Foundation. Today's webinar will discuss weather modification and look at such questions as, does the seeding of clouds enhance precipitation? We're excited to have with us today from the University of Laramie, Wyoming, Bart Geerts. Bart is a professor at the Department of Atmospheric Science for the University of Wyoming. He received his PhD from the University of Washington in 1990 and worked in Australia and in Europe for several years. Since his research deals with orographic and convective precipitation systems. Welcome, Bart. It's a pleasure to have you with us today.
Thank you, Zach.
Alrighty, so the screen is yours.
Okay. So, seeding clouds to enhance precipitation, does it really work? I very much appreciate the opportunity to talk about this. Here in Laramie, we already have a couple of inches of snow on the ground, and it is below freezing, so winter is here. Here in the western United States, cloud seeding has been conducted for many decades, since the 1960s or so. Basically, two types of precipitation activities, precipitation-making activities have been used or are being used. What I will be talking about today is cloud seeding, whereby nuclei are being injected into cloud. And then also artificial snow making, where water is sprayed under high pressure into the cold air. The water contains ice nuclei, in particular Pseudomonas syringae, a bacteria, so that tiny droplets that are ejected from the gun freeze immediately upon exiting the nozzle. And the air can be dry. You don't need clouds for this, so it's not cloud seeding. Snow falls typically within the ski area, within 100 feet or so of the snow gun. What I will be talking about today is cloud seeding, whereby clouds are seeded with nuclei so that cloud droplets become precipitation size, rain or snow. You do need clouds, so the air needs to be saturated, and precipitation enhancement may occur many miles downwind, typically 5 to 20 miles or so. And in most cases, mountains are targeted, although in some cases, convective cloud thunderstorms can be targeted as well. So this is a type of advertent or an intentional weather modification that has been going on for quite some time. I'd like to start with an introduction of clouds and precipitation. So a typical raindrop is the size of about 2 millimeters, whereas a typical cloud droplet is 1/100 of diameter, 0.02 millimeters. And a typical nucleus is another 100 times smaller. Now, clouds consist of tiny droplets. These droplets are so small that they have no significant fall speed. Typically, you find tens to hundreds, sometimes over 1,000 droplets per cubic centimeter, just floating with the wind. Whenever the air becomes saturated, you will see clouds forming because there's an abundance of cloud condensation nuclei. And interestingly, these droplets remain liquid below the freezing point for some time. The growth of these droplets by condensation is rather slow, especially when they reach a size of about 20 micron, 0.02 millimeters, which is why most cloud droplets are about that size. In fact, if you look at these two different sizes, cloud droplets versus raindrops, you can see that it would take 1 million collisions for a raindrop to form simply through the collision coalescence process. Now, clouds also may contain ice, and this ice typically is not the result of homogeneous nucleation, because it requires very low temperatures, below -39°C, but rather the nucleation occurs on a foreign particle, an ice nucleus, and that's referred to as heterogeneous nucleation. But while there's an abundance of cloud condensation nuclei, there's a rather dearth of ice nuclei in the atmosphere, natural atmosphere. This nucleation can occur through several different methods, as shown in the figure in the upper right. It can be the result of an ice nucleus, this little brown pot-shaped icon, being immersed in a cloud droplet, a supercooled droplet, that at some point, for instance at -10°C, activates to become an embryonic ice crystal. The nucleation can happen by deposition, simply vapor deposition onto the aerosol, into the ice nucleus, and it can be by contact, whereby an aerosol comes in contact with the supercooled droplet and then starts the glaciation process. In most cases, the liquid phase, so immersion and contact nucleation, occurs. So those are natural cloud processes, and these embryonic ice crystals can grow to beautiful snow crystals. In the absence of rhyming, you can have beautiful sector plates, for instance, or dendrites, or rosettes. These are laboratory-grown ice crystals. In reality, it's rare to find such beautiful crystals in nature, in part because rhyming often happens, whereby a supercooled droplet just falls upon and freezes upon an ice crystal, and in part because of aggregation of multiple ice crystals into a snowflake. The growth of these different shapes is temperature dependent and also dependent on the supersaturation shown on the vertical axis. Dendrites, for instance, form at a temperature around -12, -15 Celsius, as well as sector plate, whereas hollow columns and needles tend to form at a lower temperature. What I want to highlight here is this line, the water saturation line. What that is the relative supersaturation of water relative to ice. Ice essentially has a lower vapor pressure adjacent to the crystal than water. And as a result, you have a growth process from the liquid phase to the ice phase. Now, supercooled water is quite common in clouds. It's perhaps more common than most of us realize, and you can see that in mountainous environments, for instance on Mount Washington. Aircraft flying through supercooled clouds, they can accrete a lot of ice on the, for instance, the radome of this aircraft here, on the wing, the leading edges of the wings, and in fact that's an aviation hazard, and aircraft are equipped with de-icing devices, heating systems, or boots at the leading edge of the wings to remove that ice. And especially the larger supercooled water droplets are a serious aviation hazard that has led to several accidents in the last few decades. So I mentioned this growth process from liquid to ice, and that is shown in the cartoon on this slide. It's referred to as the Bergeron process, or the Bergeron-Van Dyson process, whereby cloud droplets are relatively oversaturated compared to ice or an ice crystal if it forms through any of the nucleation processes that I've mentioned. That ice crystal will grow at the expense of this surrounding droplets, which are far more numerous typically, such that the droplets will evaporate and the ice crystals will grow by deposition or vapor diffusion. This Bergeron process can be relatively fast, especially when a lot of ice crystals form. And in fact, it could be enhanced if more ice crystals are introduced into the cloud. So two types of cloud seeding methods are commercially used at this time, and they have been for some time. One is hydroscopic, whereby large nuclei, such as sea salt, hygroscopic nuclei act as condensation nuclei and grow to droplets the size of not 20 micron in diameter, but more like 50 to 100 micron, in which case they can jumpstart the growth of droplets by collision coalescence, because the larger droplets have a fall speed relative to the smaller ones, so they can start collecting the smaller droplets on their way down. Hygroscopic seeding is being conducted, but most typically in warmer places where clouds are too warm really for glaciogenic seeding. Glaciogenic seeding really requires cloud temperatures below -5 or below -8 Celsius. Hygroscopic seeding, well, there have been a number of studies proving or suggesting that they are effective, but in my opinion, their effectiveness has not been proven. More widely conducted in the last few decades is glaciogenic seeding, which involves two different methods: either homogeneous nucleation by the injection of dry ice, carbon dioxide, at -80 Celsius. It's solid in that state. You can buy dry ice at a grocery store to keep your frozen goods cold, for instance, to say dry ice. Liquid propane is also used. So locally around the dry ice pellets, you'll find very low temperatures such that homogeneous nucleation occurs. Ice crystals will form from cloud droplets irrespective of the presence of cloud condensation nuclei. The other method involves ice nuclei. Typically silver iodide crystals are used, and as you can see in these illustrations, the silver iodide crystals are being dispersed pyrotechnically from an aircraft or from the ground. AGI tends to nucleate at temperatures below -6 to -9 Celsius. In fact, the nucleation efficiency increases with decreasing temperature. So this is most commonly used in cold clouds, such as winter storms over mountains, or high up into thunderstorms, well below the freezing level. Here's an example of a propane burner that mixes the seeding agents and then disperses it from the top of this tower. Typically these units are remotely controlled, so they can be turned on at the turn of a switch by a controller, and the solar panels provide power, and there's communication to these towers. So two clouds are typically targeted for glaciogenic seeding, which is what I will focus on. One is thunderstorms. And the main effect that is being invoked here is that thunderstorms in a zone below the freezing level, 0 Celsius, and a lower temperature, for instance, -10, -15 Celsius, may not have any ice in it. And in order to jumpstart that freezing, ice nuclei are inserted such that latent heat is released by the conversion from the liquid to the ice phase, and that latent heat may give an extra boost to the thunderstorm, making the storm deeper and also producing more precipitation. At least that's the theory. It's also used to mitigate or prevent hail damage. The idea there is that more ice crystals will lead to smaller graupel particles. Graupel particles are heavily rimed snow crystals. And so basically there are more ice crystals competing for the same amount of supercooled water, so the hailstones are not going to grow as large. The other target clouds in the western US and elsewhere are orographic clouds. Here the static effect is being used. And the idea here is that without ice crystal, the clouds would simply rise over the mountain and then evaporate on the lee side. As for instance, the higher clouds that you see over the mountains and in the lee of mountains you see these lenticular clouds. Basically, they're liquid on the upwind side, and they may turn into ice on the downwind side at sufficiently high elevation. Anyway, if they're relatively low, they stay liquid even, though the temperatures may be below freezing, and they don't produce any precipitation. So by the injection of ice crystals or ice nuclei that produce ice crystals, the Bergeron process can be jump-started. And it's that kind of process that, for instance, Weather Modification Incorporated, based in Fargo, North Dakota, uses to promote its business to enhance precipitation. So here are some slides from Weather Modification, and I've modified the text a little bit, but the slides come from Weather Modification. So if air is forced over a mountain barrier, it cools, of course, adiabatically, first dry and then moist adiabatically. And in the lee, the air will descend warm and dry. So a cloud will form, and these small cloud droplets will form. And in the absence of any glaciation from above, natural seeding from above, from a deeper cloud, or glaciation from below, ice crystals can be introduced from the surface below. These cloud droplets may not freeze at all, and the cloud droplets would simply evaporate in the lee. But the injection of ice nuclei may enhance the precipitation process. So natural ice nuclei concentrations are exceedingly rare. That has been demonstrated sufficiently, I believe, and accepted in the scientific community. There's just few natural ice nuclei out there. So whereas naturally the first ice may occur here at the red dot and the first snow over the mountain, you may, here in yellow, introduce the first ice further upwind in the cloud at a slightly higher temperature, allowing ice formation to begin sooner and allowing the Bergeron process, or maybe the rhyming process, to grow snow from an earlier stage, in the end yielding more snowfall upwind of the crest, because any snow that falls downwind of the crest is most likely to evaporate on its way down. So in the western United States, as you know, there's vast areas with little precipitation. This shows the annual mean precipitation of the western U.S. And there's many places, all those places in orange, having annual mean precipitation less than 20 inches, which may be inadequate for unirrigated agriculture. Most of the agriculture in the western U.S. is supported by irrigation, and the water for that irrigation comes from the mountains. You can see the mountains on this map. More precipitation on the coast, of course, but then inland, every maximum that you see on this map corresponds with a mountain range. You can probably identify several mountain ranges in the interior west. So especially the southwest has experienced water shortage as population increases. And there are big questions regarding water availability in a changing climate. Here are two examples of model output. Expected trend of precipitation in the winter, December, January, February. Two different models showing, well, both of them show an increase of precipitation in the southwest in the winter. But there's much uncertainty there. Here's another model from another image from a more recent model, CCSMA2. These are general circulation models being run in the current climate and then in a future climate. This one is 50 years from 2000. So the difference between 2050 and 2000 is shown for 6 cold season months. And this is just focused on the interior west from Utah to Colorado and further east, with blue and red indicating an increase in precipitation and yellow indicating a decrease. So winter precipitation may increase, but there's much uncertainty, and also summertime precipitation or precipitation minus evaporation may well decrease according to these general circulation models. So there's much uncertainty about water availability into a changing climate. When we deal with water shortage, we can either reduce our water consumption, and much effort has been made in that direction. We can also increase water production, and this is something many agencies work on in various ways. And for the Colorado River Basin here, you can see various efforts to increase water production by reducing evapotranspiration, and that involves vegetation management. There's also been thoughts about somehow covering up reservoirs like Lake Mead. One can also recycle water more by using brackish water or recycled wastewater, and then along the coast one can use ocean water. Groundwater losses can be reduced. Groundwater storage commonly happens in Arizona in particular, and then basically a bank account for later use of the water. System outflow can be reduced, although there's very little water crossing the border from the Colorado River into Mexico, and that is constrained by a treaty. So I don't think there's much leverage there. Adding to the inflow, coal bed methane production, that's probably relatively temporarily. So there's really few options out there, and that's why many agencies, commercial interests also have looked at weather modification as a way to enhance the precipitation, rain or snowfall, through cloud seeding. And in fact, a lot of precipitation augmentation activities are being conducted in the western U.S. And this just shows western U.S. and Canada weather mod programs in 2006 in various states. The various target regions are shown in dark blue. And most of these activities are to enhance the snowpack precipitation. Some of them are to suppress hail, as you can see, especially in the Great Plains, where damaging hail is not uncommon. So it's remarkable that so many cloud seeding activities are out there, are being conducted, even though the scientific consensus on weather modification is rather mixed. There's really no consensus. You may have heard, or you may have your own opinions on this. But for instance, the National Research Council had a report in 2003, the latest of several reports, being rather critical of the evaluation of cloud seeding. The fact that so many commercial interests remain active to enhance precipitation is just a testimony to me that the water is really valuable. It's one of the most valuable commodities in the western U.S. And you know, even operators will say, even if the claims of 10 to 20% precipitation augmentation is not valid, just a 1% increase is sufficient to justify the cost of these activities, ground-based or airborne activities. I mentioned this report on weather modification from the National Research Council in 2003. It states that notwithstanding several decades of research, scientific proof of the effectiveness of cloud seeding remains lacking. It's a catch-22 paradox. On the one hand, the federal government is not willing to fund research to understand the efficacy of weather modification technologies. And in fact, after 2 decades of heavy investment by the federal government, especially the Bureau of Reclamation, also NSF, National Science Foundation, in support of weather modification in the 1960s, 70s, and early 80s, federal agencies have stopped funding weather modification research in the last 25 years or so. So Federal government is not willing to fund this research, yet private interests are willing to spend funds to apply these unproven techniques. The 2003 report advocates a renewed commitment in federal funding to support weather modification research and recommends that opportunities offered by these operational weather modification programs should be capitalized upon to do fundamental research. And in 2008, Nature magazine, as you know, Nature and Science are on top there in terms of quality peer-reviewed research. They had an editorial, and this was in advance of the Summer Olympics in Beijing. And you may have heard that a lot of cloud seeding took place around Beijing during the Olympics, especially during the opening day, when the government there did not want any rain to fall on the Bird's Eye Stadium in Beijing. And in fact, they succeeded. And it remained dry that day, but it's not clear whether that's because they seeded the thunderstorms in the vicinity. Anyway, the Nature magazine states in their editorial that other countries such as the United States have simply given up. The most promising experiment in America is run not by the federal government, but by the state of Wyoming, which is spending $9 million. Actually, now it's over $12 million on a 7-year series of cloud seeding experiments evaluated by experts from the National Center of Atmospheric Research. And they state that's the type of targeted and rigorous study that is needed in weather modification, but it took Wyoming to do it. They also state that the stakes are high, as weather modification is one of those areas in which science can have an immediate and obvious benefit for society. It's long past time to invest modest funds in the basic understanding of it, as long as this science, of course, is rigorous quality science. And that brings me to the question, can we really trust peer-reviewed publications? And I was intrigued by an article in NPR, on NPR. You may have listened to this, all things considered, on the 3rd of October of this year, when science contributor John Bohannon sent a deliberately faked research article to 305 different online journals. More than half of the journals that supposedly reviewed this fake paper accepted it. And you can listen to this NPR article. It's very interesting, and it's also sobering. So we have to ask fundamental questions, and I'm going to apply these basic questions to the research dealing with weather modification. Is the analysis objective? If an organization funds a research project that will benefit them financially, then we cannot accept the findings as evidence unless different independent researchers come to the same conclusions to their own independent research. And that brings us to the question of repeatability. And in weather modification research, it is very difficult to repeat an experiment as it can be done in medicine, for instance, simply because every storm and every cloud are different. Are the data representative? Publications may not show all the data. It's crucial for researchers to ensure that the data they collect is representative of the true situation and is not some sort of subset to prove a point. And there's also a question about the robustness of the peer review process. Fundamentally, peer review means that other scientists who specialize in that particular research have verified the quality and validity of the research. And some journals are better at this peer review than others. Many of the journals that reviewed this fake paper that science sent around probably were low-quality journals with a very low rating of the ISI Science Citation Index journal impact factor. Many of them now are online. Open access journals. Many of those publishers probably are predatory publishers, as the NPR report mentions. In fact, it's just a scientific method, not very different from these phishing emails that you may have seen from Nigerian individuals that are offering their help with their transfer of money from some Nigerian source to your bank account. But nevertheless, peer review may not be as robust as we think it is. It's very difficult for editors, and I've heard this from several editors, to find reviewers willing to make the effort to really take the time to rigorously review a paper. So hundreds of peer-reviewed papers have been published on weather modification research, especially in the 1960s, 70s, 80s. It started back in the mid-1940s, and I'm going back to that because I'd like to question that work, and I'm not the only one to question that work. The work that really instigated the whole weather modification business. So scientists at General Electric Research Lab in New York, upstate New York, I believe, they demonstrated that dry ice, and then later also silver iodide, with a crystal structure similar to that of ice, can initiate ice in a laboratory supercooled liquid cloud. And later on, they took this out into the field when they dropped dry ice pellets, or AGI nuclei, from an aircraft into supercooled stratus clouds. They found that the cloud cleared. This is work by Vincent Schaefer and Bernard Vonnegut in the year shortly after World War II. And in fact, they used World War II bombers, modified bombers like the B-17, to drop these dry ice pellets and silver iodide nuclei. From here you can see scientists collecting dry ice in bags that were then dropped to a porthole in the aircraft, flying over supercooled stratus cloud layers. Here's an image of Vonnegut, Schaefer, and Langwer. So here are some images. One image is the photograph of a seeded cloud. They did a pattern, a flight pattern. You can see the flight pattern quite well. A B-17 flew about 100 meters above cloud top. This cloud top temperature was below freezing, but not much below freezing, -6. And the cloud cleared in several occasions. Here's a relatively thin cloud, and you can see how the cloud entirely clears, and you can see something that may be ice falling down close to the flight track. Persistent cloud edges are shown on the left and the right. They claim that the thin cloud disappeared simply because ice crystals formed that consumed the available liquid water and possibly water vapor. But that's based on photographic evidence only. Back then they did not have remote sensing probes or in situ probes on the aircraft to really document the changes in droplets, size distribution, the formation of ice, etc. Here's another image showing, it may be difficult to see, but there's a line through this cloud, relatively deep stratus cloud here, widening gradually. This is an image that Chris Walczak at University of Albany gave me. So was the glacier genic seeding really responsible for the observed cloud clearing back in the 1940s? So what happened is dry ice was crunched into centimeter-sized chunks and dropped from the aircraft, a porthole in the B-17, yielding significant spacing between individual falling pellets of dry ice. That spacing was probably irregular, but was several meters given the speed of the aircraft. The question in my mind is whether the resulting ice crystals, embryonic crystals surrounding the dry ice, really grew into snowflakes, consuming the supercooled liquid water and yielding these open paths in the cloud. Chris Walczak recently proposed that the aircraft's downwash could be responsible for the clearing of the cloud. These are fairly heavy aircraft they used. The B-17 with a fairly large wing surface area, and that can produce a downwash not unlike the downwash that's seen in this image. And that can trigger something called cloud drop entrainment instability, whereby the droplets simply evaporate. Here's an image of how that works. You need to have a certain temperature lapse rate, an inversion, and a mixing ratio. So dry air, loft, moist air in the cloud, the shaded area is the cloud. And then when an unsaturated parcel is entrained into the cloud from aloft because of some disturbance, for instance a downwash from an aircraft, it cools rapidly by the evaporation of the cloud droplets. That's an entrainment process. And then this cooling can be sufficient for this parcel to be negatively buoyant, and then it can be accelerated further downward, drawing the dry air from aloft with it and opening the cloud. This is an instability that is important also in the maintenance of marine stratus over subtropical oceans. Another possibility is that Schaefer's and Vonnegut's cloud clearings were actually the same or very similar to the cloud holes that are often punched through supercooled stratus clouds by aircraft. And you may have seen some publications on this. Andrew Heimfield at NCAR recently reported on that in Bands and in Science. These images, or at least the upper right image, Morris image, is from that publication. Propeller aircraft, the engine propellers at the tips of the propellers, there's sufficient adiabatic cooling because of the pressure drop that locally you have temperatures below -39 Celsius, in which case you have homogeneous freezing, and so the supercooled droplets turn into ice instantaneously, yielding a trail of ice crystals behind the aircraft. And that process then can lead to basically aircraft-induced seeding, rather than seeding by anything that was dropped from the aircraft, like silver iodide or dry ice. So in a way, our commercial aircraft fleet can be far more efficient, in fact, than any intentional advertent weather modification in turning supercooled droplets into ice. Whether it enhances precipitation, that's of course another question. Typically these clouds are relatively thin, and any resulting ice crystals may sublimate before they reach the ground. Anyway, back to the question of trusting peer-reviewed papers, especially on the topic of glaciogenic cloud seeding. I think several of the papers have made statements that need to be considered with a grain of salt. Back in 1981, there was a paper, radar detection of cloud seeding effects by Hobbs et al. At University of Washington in Science. And it shows maybe the first, or one of the first color images of a profiling radar, Ka-band millimeter wave radar. And this red band here, as you can see, dry ice, let's see, a portion of the cloud that was artificially seeded with dry ice produced a more intense radar echo and a trail of precipitation that reached the ground. The ground being down here at the bottom. This is a vertical transect. I think this was an aircraft flying with this. No, it was an aircraft seeding using dry ice. A very low concentration of dry ice, though. The quoted seeding rate is just 0.05 kilogram per kilometer along the freight track, which implies a typical spacing between the dry ice pellets of 50 meters. And it's quite possible that instead of the dry ice, it was instead the propellers of the aircraft that produced ice crystals. The same authors then later wrote a paper on aircraft-induced ice particles, or APIPs, aircraft-produced ice particles. So now, given that this is a single observation in a rather short paper, I would be skeptical about it. Here at the University of Wyoming, in the last few years, we have looked at radar profiles similar to the ones shown here, but far more detailed, both profiling and actually also scanning at millimeter and centimeter wave. looking for plumes of enhanced reflectivity downwind of silver iodide generators, and we did not see, not even once, well-defined plumes of enhanced reflectivity in the orographic clouds that we targeted in some 30 intensive observation periods over mountains in southeastern Wyoming. So given the singularity of this observation, I would be skeptical. Questions must be asked about the persistence of this feature, the repeatability, and the uniqueness of a feature such as this one in a precipitation system, in the storm system. Precipitation, as you know, is one of those fields in atmospheric sciences that it's essential. Precipitation is very important in society, economy, but at the same time it's highly uncertain and highly, should I say, noisy, both in space and in time, so difficult to measure. So back to the question, can we trust peer-reviewed papers on glaciogenic cloud seeding? In the 2001 opinion letter in Banff, Peter Hobbs himself was critical about weather modification research, and he states that the public deserves a more straightforward statement on the uncertainties of cloud seeding to increase precipitation. In my opinion, and I share this opinion with several others, cloud seeding literature in the 1960s through 1980s, maybe not all of them, but many of them are a monument to subjectivity. They often lack peer review by outsiders, that is people not involved with the cloud seeding activities. Many of the reports were bogus, and some of the findings were exaggerated. In my opinion, this is evidence of short-sightedness. In the long term, it probably hurt the cloud seeding activities, and in fact, it may have contributed to the end of federal funding for weather modification research in the late 1980s. The fact is, as I just mentioned, that precipitation is an extremely noisy field, and it's very difficult to accomplish meaningful control versus target experiments. So is there any hope? Well, the 2003 National Research Council report encourages larger randomized experiments with a stronger statistical basis, as well as physically based experiments to improve our understanding of the changes in cloud microphysical and dynamical processes resulting from the cloud seeding. And in fact, both types of studies have been conducted recently. Several rigorous statistical studies have come out recently. For instance, Morrison, Manton et al. Work in Tasmania and the Snowy Range of Australia. And recently, the National Science Foundation has funded a study to examine cloud processes in seeded clouds using new observational tools as well as high-performance computing in the context of this ongoing Wyoming weather modification pilot project that I mentioned. And this is conducted over 2 mountain ranges in southern Wyoming, 2 different mountains. It's a double mountain blind randomized experiment that is actually continuing through early 2014, and results of that project are not out yet because all cases are not available yet. They hope to collect more cases this coming winter, and then a report should be due later next year, about a year from now. And NSF supported basically cloud microphysical observations in the context of this project. We used Wyoming King Air with various instruments, in particular a in situ instruments and also a cloud radar, vertically profiling radar. And we did several flight legs. Here's a symbol of the aircraft across the mountain range, both before seeding and during seeding. And the generators we used, they were located just downwind of the first flight leg. So the first flight leg serves as a control. The 4 other flight legs over the mountain, legs 2 to legs 5, they were target legs. And seeding plumes are shown schematically. So there's a no seed period typically preceding a seed period. And we've reported on this in the literature. And there is circumstantial evidence that this seeding does enhance reflectivity close to the ground within the well-mixed planetary boundary layer where we expect it, simply because ice part, or rather AGI nuclei are not going to be mixed any higher than the PBL, the planetary boundary layer. We look at both comparison between the seeding and the pre-seeding period. In the target area, we also compare the seeded area to the, or rather the target area to the control area. But there's a lot of uncertainty in these studies. The number of cases is relatively limited, and the case-to-case variability is rather high. Some cases show a strong reflectivity increase near the surface over the target area, and others actually show a decrease relative to or compared with the changes that occurred over the same period in the control region. So I think I would like to leave it with that. I don't have any conclusions, but just to summarize, I'm not going to delve in this more. We have these detailed observations that were not available back in the days when the federal agencies funded weather modification research, such as this transect of radar reflectivity over the mountain range, LiDAR data, vertically profiling LiDAR data. Also, there's very high resolution large eddy simulation cloud resolving modeling activities going on at the National Center of Atmospheric Research that, in combination with the observations, should shed light on the cloud microphysical processes that take place in association with the introduction of silver iodide nuclei from the ground or from an aircraft. So we're in a better position now than we were a few decades ago to do fundamental research and to look at basically to X-ray clouds to better understand the cloud processes leading to any changes in precipitation that may or may not occur. This is work that the University of Wyoming is hoping to do, or is currently doing, and hopes to continue to do in collaboration with NPR, as I mentioned, and several other universities. So there is some hope, I believe, but as I mentioned, the research needs to be done very carefully, very rigorously, so that we don't fall in the same trap that the research fell into in the last few decades, being overly optimistic, maybe in publicizing results that may not have been rigorously analyzed. So I will leave it with that.
Alrighty, thank you, Bart. That was great. So now we'll go ahead and begin our question period, if you don't mind. We'll start taking some questions, and if you have any questions, please be sure to give your name and your state. We will go ahead and ask Bart any questions. And while they're starting to come in, I do have a few questions. My first one is with the silver iodide cloud seeding. Is there any study on does it change the snowflake type or the flake size or anything with the flake compared to just a regular snowflake?
I don't think it will change the snowflake habit, simply because it is, in essence, a nucleus, just as any other nucleus that naturally may exist, that only initiates the ice crystals, and then the crystals will form around that nucleus in a certain shape depending on supersaturation and especially temperature. For instance, dendrites typically form around -15 Celsius, needles form at -25 Celsius. Irrespective of the type of ice nucleus that initiated that crystal.
Okay, thank you. I have a question coming in from Jim in Grand Junction, Colorado. I'm not really sure what this word is, the meta-hide and other organic seeding nuclei still being used in some areas?
Not that I'm familiar with. Liquid propane, dry ice, carbon dioxide, silver iodide, and then hydroscopic particles in warm clouds. Those are the ones that are most widely used. Acoustic techniques have also been used, but I don't think they work. Basically, some explosion in the cloud, making a loud boom sound, and yeah, I don't think they work.
Okay, thanks for answering that sound one. That was actually the next question from Chuck in Indiana, so I think you took care of that one. We have had some hail suppression studies down here in the San Luis Valley in southern Colorado with that as well, but I'm not really sure what they found to try and break up those hailstones. Alrighty, I have a question from Jim in Missouri. Does cloud seeding have an effect on reducing intensity of hurricanes?
Oh, this goes back to an experiment in the 1960s, I believe. Storm Fury, F-U-R-Y. May want to look that up. This was federally funded, and the hope was that cloud seeding would suppress hurricanes by introducing additional ice crystals, and somehow that would diffuse the storm's intensity. This was abandoned fairly quickly. I think one reason is that it's impossible to really demonstrate that ice crystals introduced by these ice nuclei, these artificial nuclei, have any effect, since hurricanes, their evolution are so complex and tied to various factors that were certainly not well sampled back then. So, and it's not like you have two hurricanes, one next to the other, and behaving identically, one being seeded, the other being in control. That's one thing, and the other thing probably is that any advertent weather modification can yield lawsuits. If you somehow change the hurricane's track by seeding it, then you may be held liable for any damage that may occur in the actual landfalling area. So that was abandoned fairly quickly. There may have been efforts since then, but no serious ones to my knowledge.
Okay, thank you. Another question is has there been any studies on possible impacts downstream? So, pretty much the stealing of water for folks downstream.
Yeah, this is a question that comes up frequently. Whenever cloud seeding is being conducted, the communities downstream will ask that question. These high-resolution numerical simulations show, not surprisingly, that silver iodide, when it is ejected from generators, will float over the mountain, and in the absence of any clouds, they will just make it over the mountain and disperse downwind, and they in fact may enhance precipitation downwind if there are clouds downwind, because they, as long as they remain airborne, they can serve as ice nuclei, and this can happen any distance downwind. The first substantial clouds, I suppose. But then when these ice nuclei are released in target clouds, and this is what happens in practice, not in the clear atmosphere, but in clouds, then it turns out that these ice nuclei are quickly absorbed, either in the cloud droplets themselves, or in, well, they can act as ice nucleus, or they're simply absorbed in the precipitation, and they are being removed with deposition, essentially, over the target mountain range or the target cumulus cloud fairly effectively. The modeling suggests that there's very little chance for significant impact downwind. To really demonstrate that with observations, I think, is virtually impossible, simply because you're talking about a second order uncertainty. The first uncertainty that we're still coping with is cloud seeding over the target area effective? And next, we're dealing with much smaller concentrations of silver iodide over downwind areas. Anyway, the modeling suggests that these effects should be insignificant.
Okay, thank you. A question from Janice here in Colorado. To avoid problems with propeller turbulence or aircraft motion, could tether balloons be used for cloud seeding at extended periods?
Well, there's a great idea. We may explore that. Yeah, actually, the research aircraft we have at the University of Wyoming here has modified propeller tips that supposedly avoid generating ice crystals along the tips, under most conditions at least. But yeah, a tethered balloon is a good idea. It's certainly difficult for ground-based generators to effectively mix the silver iodide nuclei into cloud. These generators have to be high enough, yet you don't want to put them on mountain tops because it's too late at that point. The generators have to be upwind of the target mountain range. So they have to be high enough to be above cloud base, but not be on the mountain top. So releasing silver iodide from higher towers or from a tethered balloon might be a good idea, simply to get silver iodide into a cloud, as well as to avoid these aircraft-induced ice particles that the questioner asks about.
Excellent, thank you. And I think we have one more question coming in. While that's coming in, I think I saw a question at some point saying, is there any environmental impact with the silver iodide coming down?
There are studies on that. So I have a slide here. I don't know whether you can still see my screen. Is silver iodide an environmental hazard? Natural background concentration of silver in streams is at least 2 orders of magnitude larger than the man-made source, at least over the target mountains in Wyoming. And this is work that, as part of this Wyoming pilot project, was contracted to the Desert Research Institute. So they actually sampled the snow in target regions, looking for trace chemicals, in particular silver, compared their concentrations to background concentrations and also to concentrations of well-correlated other chemicals such as cesium and rubidium. And they found those concentrations to, well, in some cases they could be measured as being higher, indicating that yes, this target area really is a target area. But then in the runoff in spring, no difference could be found between target regions and watersheds that were not affected by the seeding, simply because natural erosion of silver from the rocks is predominant.
Okay, thank you. And kind of a follow-up question to that one from Kendall in Kansas, and you may have mentioned this as I was reading this one, so I apologize if I'm repeating this one, but would there be the ability to find trace amounts of the AGI that fall within the precipitation to prove that it's actually working?
Yeah, and that is in fact the strongest evidence we have that indeed the target area is effectively targeted, that silver iodide modified snowfall does fall in that target area. So whenever we make measurements at the ground of snow crystal size distributions or habits or total snowfall amounts, we also sample the snow for chemical analysis to make sure that the snow has enhanced concentrations of silver in it. So the answer is yes.
Excellent. That's great. Well, I think that's all the time we have for today. Thank you so much for joining us today, Bart. That was very, very useful, and I'm sure everybody else with us enjoyed it. And thanks to everyone else who joined us today on our webinar. Please make sure that you join us for our next weather topic webinar, which is actually next week. It's a special webinar on Thursday the 14th with Greg Carbon of the NOAA Storm Prediction Center. Greg will give a review on the significant weather events that occurred in 2013. There's been quite a few, including one very close to us here in Colorado with our floods, and it even hit you quite a bit up in Laramie too as well, Bart.
Yes.
So that will be a very interesting webinar. And my last note is, please, again, as you're leaving the webinar, make sure to take the survey that pops up. Again, that'll help us out greatly. And once again, thank you so much, Bart, and we really enjoyed that. So thank you, everyone.
Thanks for the opportunity.